Okay, today we're going to be discussing the memories of the processor that we're going to be using, starting off with the working registers. They are R0 through R31. So there are 32 working registers. These are what handle the work. That's where the work is done. Now, there are some special registers, R16 through R31, can do anything. Any instruction can be executed on those 16 registers, upper 16 registers. Some instructions don't work on 0 through 15. So the convention is to start working, when you're writing a program, start working with R16 and move up as you use more registers. R28, R26, R27, 28, 29, and R30 and 31 are your X, Y, and Z pointers. A pointer is used to point to an address in memory. So since the addresses are 16-bit, the memory addresses are 16 bits, you need 2 registers to point to them. The R26-27 pair, 28-29 pair, and 30-31 pair. The high byte of the address is the higher register number. Low byte is the lower register of the pair. So you would load or calculate an address to put into the pointer registers, and then use a load or store operation that accesses those pointers. So we'll get into load and store operations a little bit later. But keep in mind the registers that can do different things, but they're all 8-bit. So just a number from 0 to 255. So yeah, those are the main issues you need to understand about the working registers. So we'll go to the regular memory of the processor here. Get to the table of contents here. Memory overview. Memory size. Memories. Memory map. We looked at this one before. You have two different memory spaces that you're going to deal with. The program code space, the program memory, and the data space. The program memory, you're going to program that with the IDE, and from there it'll load into through the USB into the chip and run the program when it gets powered on. The data space is the part that you use during the operation of a program. It is a 16-bit data space. Some of it is reserved that you don't use. Some are beyond the scope of this class. Let's see here. You know, these you don't have to worry about. Your EEPROM is your non-volatile memory. And then this is your working RAM, which I believe we're only going to use on the third project. But they're all addressed the same way. The store and load operations for the I/O registers, the single cycle and the extended I/O registers, are addressed the same as your RAM. They're on the same map. So the same process is used for both. It's just a matter of when you write to the I/O registers, you will be accessing the various peripherals of the device. Whereas the static RAM is just for storing data. So yeah, it's all accessed the same. But let's see here. Now, going back to the whiteboard here, there are some important memory addresses to remember that we'll be using. Locations, to remember. Port A has a base address of 0x0400. Port C, we're not going to use port B, is 0x0440. And port D is 0x0460. The type A counter, which we will be using, type A counter, timer 1, or 0 I should say, has a base address of 0x0A00. We'll get to some later in the as we go along. We'll get into the addresses of other peripherals that we will be using. But for the most part, we're going to be using the timer counter and ports A, C, and D. Now, what a base address is where the registers begin for that peripheral. So, for example, port A has, I want to say 15, 16, maybe 20 registers associated with it to control that register. Those have a base address of 0x0400. And then each of the each of the control registers have an offset from that base address, which you just add to the base address. So you can load the base address into one of the X and Y or X, Y, or Z pointer registers, and then add the offset to that, and then you can load and store from those locations. So let's go back to the data sheet, and we'll go, let's go to the, this is quite cumbersome. Let's go to the ports, peripherals and architecture. You see the peripheral address map. The base address for all the peripherals are there, but we'll go looking at that at this point. Ports. All the ports are here, and they all work the same. So you get a you have, oh, it's a 23 or 24 registers for each port. You see, each port, each register of the port has an offset that you add to the base address to use the access those port registers. So, for example, the DIR register is the direction register, determines whether or not a pin on the port is an input or an output. The out register, if it's an output, will output those values to the 8 pins of the port when data is written to the out register. To read the status of the port, if it's an input or if it's an output, you can read the in register. You can individually control the interrupt enable, or no, the invert enable, whether it's a pull-up register, uses the internal pull-up resistor, and configure it as its interrupt sense control, each individual pin of the port. But keep in mind the offset, that's not the memory location. You have to add those numbers to the base address of the port that you're using to get to those registers. So load the base address into the pointer and then add these offsets to get the address for the individual registers. Now there are some registers that there we go. Come on. Come on. There you go. Why don't they have the memory map? The first 64, I believe it is. First 64 registers, I/O registers of the data space, can be accessed in a single cycle using the in or out command rather than a load and store. We'll get into that as we go along in the actual programming segment of the semester. But those in and out commands only work on registers on the memory locations from 0000 to 003F. They do not work beyond that. It will throw an error if you try to compile it with an address above those, above that number. So the extended I/O registers need the load and store commands. Let's see here. The general purpose registers. In the single cycle I/O space, there is 4 registers for general purpose use. They don't control any peripheral. They don't control the CPU at all. They're just general purpose data storage that you can access in a single cycle. The general purpose registers are at 0x 1C, 1D, 1E, and 1F. They can be accessed with the in and out instructions. They're for holding temporary data. I've used them in the past to hold global variables that are accessible anywhere in the program by just using the in or out command. But those are available for use for storing data in addition to the static RAM that we have down here, higher in the memory map. Let's see here. Now, we're going to go to the look at the ports again. Come on. Ports. We're going to look at the features. The ports are general purpose input and output pins with individual configuration. Pull-up resistors or inverted I/O, and inverted I/O if you choose it. It can sense both edges for increasing edge or falling edge, or both, or sense a low level. They are controlled by instances of the port peripheral registers. Each port instance has up to 8 I/O pins, corresponding to the 8 bits of the control registers. The ports are named port A, port C, B, C, etc. So each port pin has a corresponding bit in the data direction and data output value registers to enable that pin as an output and to define the output state. The input value of the pin, a port pin, is synchronized with the peripheral clock and then can made accessible as data input value from port A, for example, in register. Pin value can be read whether the pin is configured as an input or an output. All pin functions are individually configurable. Let's see here. Gives you a block diagram of the pin and how everything works. You can see the registers are use data flip-flops that we discussed earlier as memory locations. And that's the general schematic for each of the pins. Let's see here. Initialization. After reset, all inputs or outputs are tri-stated, and digital input buffers are enabled even if there is no clock running. The following steps are optional when initializing port operation. Enable or disable the output driver for pin X by writing a 1 to the direction set or direction clear register. Set the output driver for the pin to high or low level depending on what you want. Read the input pin using the port in register, and configure individual pin configurations and interrupt control with the individual pin control registers. For lowest possible power consumption, disable the digital input buffer of unused pins, and pins are used as analog inputs or outputs. For pins with the digital input buffer enabled, it is recommended to transition between high and low voltage thresholds as quickly as possible. Yeah.
I don't know how else to say this. Completely lost. So is there obviously we're gonna be like going into like programs?
Yes.
So are we able to maybe like an example or
an example program?
Something just to like we're getting I feel like we're getting
a little bit more theory and not enough practice.
Precisely.
Okay. I was trying a different approach. Sorry about that. I do not have a example program on this flash drive, but I can have something on Friday. Come on, a little bit late, but yeah, it's I'm just trying to been trying to get you familiar with the hardware that you're going to be dealing with, and the process by which you operate the hardware. I understand the frustration on your end. Getting into this initially is kind of challenging, and assembly programming is challenging because it is very tedious. Everything that you do has to be done at very basic steps. For example, let me go ahead and come on. There we go. So a little code snippet to make pin 4 of port A output high. Okay. So you load R27 0x04 LDI R26 0x00. The LDI command loads an immediate value, load immediate, into a register. So you're just loading those numbers into those working registers. Yes.
I don't understand. But like, assembly's like the first code, right?
Yeah.
So
Yeah.
what are you typing it into?
Oh, they have compilers for them now. Initially, they had to write a compiler in machine code to translate from assembly code to.
So I'm saying, like, if I wanted to do it,
Yeah. I didn't. Well, I can go to.
I'm just trying to make it clear.
Come on. Let's see if I can get to it here. Go to micro. Come on now. I don't want to do that. Okay. Microchip.com. Microchip.com makes the processor that we are going to be using. Okay. So type in the search thing. Atmel Studio. And you get products, tools and software. Okay, come on now. Where are you? It's 7 is the version. Maybe it's been a while since I had to. Microchip Studio. Why can't? Yeah. Tools and software demo board. No. Download. Studio download. Microchip Studio. Oh, okay, here we go. Microchip Studio is the IDE that we're going to use to type in the programs, and it will compile the code that can be down and control the USB to the board that has the chip on it. So go to microchip.com and look for Microchip Studio for AVR and SAM devices. We're using the AVR device. So I can probably put the link, find the link. I have to download it again on my computer because my hard drive fried last week. So I'm going to have to go here anyway on my laptop. I will copy the link and send it out in a announcement on Canvas in the next couple of days. But yeah, that's what we'll be using to, and I'll, when it comes time for that, I'll bring my laptop in here and we'll go through the process of creating a program, how to compile it, how to download it onto a board, that sort of thing. The only problem is okay, come on. Where do you download it? Where's the download button? Am I missing it? Okay. How do you? Application Center. Okay, there we go. Download Microchip Studio. The only problem is it's only available for Windows. If you have an Apple or a Linux machine, you're out of luck. Are you a Mac person?
I have two laptops.
Oh, okay. Well, Mac only has about 20% of the market share, and they figured that's not worth the effort to develop a version for Mac. So, for this, you might have to use your Windows machine. But this link I will email or put in an announcement on Canvas. But let's go back to this, and then okay. So these are the load immediate command. Then you have the data that you want. Say you want pin 6 to be an output. So you load in R16 0x0 pin 6 1 0 0 0 0 0 0. That's bit 6 of an 8-bit field, right? So you can translate that to oh, I'm sorry, it's 0b, not 0x. That's binary. Okay, then you would store the address in the address pointed to by X, the value in R16. So you would, it's a 4-step process to get to that point. Then you would have LDI R16, or let's make it R17 for a reason there, just a second. R17 0x04, because that's the output register of the offset of the output register of port A. We will now add Word R26, R17. You're going to add the value in R17 to register 26 and 27 and store the result in R26, changing the location of that the pointer is pointing to. And then you would store X R16 again to make pin 6 of that port a high output, because here, remember, you have the high value in the 6th, in bit number 6 here. So you would output it to the port register that way. That's just to turn a pin on. So that's what, 1, 2, 3, 7 lines of code to turn the pin on. This is what I mean by tedious with assembly. It is, you have to break things down into very basic steps and then write those steps individually. Honestly, there's a lot of cut and paste or copy and pasting going on in most applications, because you find a piece of code that you're going to use repeatedly, like a housekeeping routine or something like that. Copy and paste it multiple times, you know, that sort of thing, so you can program a little bit quicker. But this is why people don't like assembly. But I will have an example program, and I can step through some of the a simple program to blink an LED once per second. I will have that on my flash drive for Friday. And I will get the IDE link posted on Canvas as well. So have a good day. See you on Friday.